This video on the equation of time is interesting, and so let's take a quick look at part of it.
The variation in the length of the solar day isn't due to the change in the Earth's rotation speed. Although it does vary a little, the effects are both small and unpredictable, whereas the variation in the length of the solar day is large and predictable. There are actually two different causes of this variation. Firstly, the Earth moves in an elliptical orbit around the Sun, and secondly, the Earth is tilted on its axis. I'll now talk about each of these effects in turn. The Earth takes 23 hours and 56 minutes to make a complete rotation on its axis. However, a solar day is on average 24 hours long. This is because during the time it has performed one rotation, the Earth has moved around the Sun a little in its orbit. For example, if we take the point in time where the Sun is at its highest in the sky, marked with a purple dot, then one rotation later, because the Earth has moved along in its orbit, the Sun isn't overhead at this point. It takes an extra 4 minutes for the Earth to rotate a little further to reach the point where the Sun is once more at its highest in the sky, and that's why a day is on average 24 hours.
Okay, so that's your typical heliocentric explanation for why there's a 4-minute discrepancy between the sidereal day and the solar day. So let's dig into this a little bit and see if it makes any sense. Okay, so here's our globe, and here's the equator. Now this is the 45-degree mark, and in 1 hour, the Earth spins 15 degrees. So let's see, right here at 60 degrees is 1 hour of time. Earth spins at about 1669.8 kilometers per hour. So between 45 degrees and 60 degrees is about 1670 kilometers. Now, if you divide that by 60, you're going to get 27.83 kilometers per minute. And to spin about 4 minutes, it's going to be a distance of 111.32 kilometers. 111 kilometers. So 111 kilometers is about 70 miles. So we'll call it 70 miles. An equivalent, I don't have a scale right here, but if this is 1100 kilometers, we've got to divide this up into 15 parts. So 1 5/8. So it's going to be less than 1/8 of an inch. It's 0.10. Let's call it 1/8 of an inch because it's not quite 1/8. But if we're going to go about 1/8 of an inch, we're going to go from here to about there. Okay? Now that's about 70 miles between those two pins. It's even a little further. But as we can see, that's not very much distance. That is the distance that a person on the equator has to travel in 4 minutes to realign with the sun. So in 23 hours and 56 minutes, he'll end up here. And 4 minutes later, he'll travel to about here. So now we're clear on how far the observer needs to spin to come back in alignment and realign with the sun. Let's have a look at just how far the Earth itself will travel in 4 minutes. As we were saying, in 4 minutes, a person would spin from here to here. Now, in 4 minutes, relative to its motion around the sun, Earth would move from that point to where the tape is at. So he's going to go from there to there. Now, how's anyone going to be able to discern the difference when they've moved 62 times further than they will have spun in the same amount of time? I'll answer my own question. They wouldn't be able to.